Hello, good evening, good day, everybody. How are you doing? I hope you're all doing very well. Welcome to the latest episode of the Ask Abhijit show. Today, we discuss science, astrophysics, technology, and all that wonderful stuff. Great to see you all. Let's see who all is there with us. Let's see. Vladimir, Adityanath, Rohit, Aditi, Amit, Suraj, Nikhil, Durga, Sarthak, Heartbreaking 40, Swapnil, Tushmita, Mr. Jesus, Rahul, Crazy Brain, Shweta, Priyanshi, Thomas, Vishal, Purobi, Sneha, Sayan, Zen, Mehul, Jay, Ashok Kumar, Gunit Dillon, Ayush, Herbie on Wheels, who is drunk in Goa. All the best. Enjoy, sir. Suraj Gowda, Ankit Negi, GK, RTK, Trupti, someone, Vishal Kumar, Dr. Nischay, Aryan Sardesai, Digvijay, Factopedia, The Walk, Paradigm Shift, and lots of other people. Great to have you all with us. Let's see some more people. R.I. Keshav, Ram, Samir, Janani, Lage Raho, Online, Divyang, Joseph Stalin, Mayan Mevada, Abhishek, Mohit, Lucifer, Morningstar, R.I. Abhijit Kamat, Hindu, Sher, Punit, Kishan, Pranshu, Somnath, RTK, and lots of other people. Great to have you all on this tonight's show. It's night here where I am. And with that said, let us get into the questions. We are discussing science and all that fun stuff. Let's see the first question. What is the first question for today? Okay, Gihan Jain says, if nuclear submarines can be made, then why is it taking so much time to make nuclear power-based aeroplanes? And there's a related question with that. What are your thoughts on nuclear microreactors? Are they a viable and stable alternate power source in resource-scarce regions for long-term operation? That's from Pranav. And the first question about nuclear aeroplanes is by Gihan Jain. So on a slightly tangential note, it reminds me of this wonderful piece of logic. Uh, it, it is said that submarines are safer than airplanes. So why are submarines safer than airplanes? Because there are far more airplanes in the sea than submarines in the air. Logic. uh, right. So that's why submarines are safer than airplanes. Anyhow, let's come back to the question. So, if nuclear submarines can be made, why is it taking so much time to make nuclear power based aeroplanes? It could be possible. The thing is, the thing about airplanes is that sometimes they tend to malfunction. Any piece of mechanical equipment, any piece of technology can malfunction. Now, if you are you have an airplane, if it malfunctions, unfortunately, it crashes. This happens from time to time. A few crashes per year we witness, right, in various parts of the world. Uh, that's what happens. Now, if you have a nuclear reactor on an airplane and it unfortunately for whatever reason crashes, you're going to have a disaster unless you make the nuclear reactor so durable and so hardy that it doesn't break open and leak out its contents, right? So that's always a problem when you have an airplane that falls from the sky for whatever reason from a few kilometers up in the sky. You're going to have a massive impact, right? And that impact could cause a catastrophe, a nuclear catastrophe, if there is a nuclear reactor on the airplane. So the solution would be, if you want a nuclear power airplane, first of all you would have to miniaturize the reactor. It's already a problem. It's already a huge technological challenge to miniaturize nuclear reactors for submarines, right? If you want to make a nuclear submarine, if you want to make it nuclear powered, you have to miniaturize the reactor. In your terrestrial, your regular reactors, and the reactors can be as big as you want them to be. Size is not an issue. You can make them large. But for nuclear submarines, every single kilogram that goes onto it matters. So you have to miniaturize it. And miniaturizing reactors just for nuclear submarines itself is a huge technological challenge. Very few nations have been able to overcome this challenge, solve the challenge. I believe India is one of those nations that have overcome the challenge. Yes, right. So it's already a challenge to make reactors fit into submarines. Now you want them to fit into aircraft, you're going to have to miniaturize them even further. And I don't think it's right now within the capabilities of any nation or any technological advance to miniaturize nuclear reactors that far, right? So that is the problem. And so there are two things. First of all, it's thus far it's not been possible to make nuclear reactors that small, as far as we know. Whatever information is in the public domain, from that I am saying that we nobody has thus far developed the capability to miniaturize nuclear reactors that much. And secondly, there's the problem of for, even if the aircraft crashes for some other non-nuclear reactor related reason, it's going to fall down, and it's going to fall from a height of several kilometers typically. Yeah, the cruising altitude for airliners, commercial aircraft, is typically 10, 11, 12 kilometers, around that altitude. You have something falling from there, it's going to break open the reactor unless you make it really really strong and durable, which would need additional weight, which would defeat the purpose of miniaturizing it. So these are the reasons why it's not been, why nobody has done it. As if I know, the Americans and even the Soviets had tried this. They may have tested this out, nuclear powered aeroplanes. Now see, nuclear reactors can certainly be carried in aircraft. Yeah, if you have large enough aircraft, so you could use that to power the aircraft. There's also the concept of nuclear powered ramjets and scramjets, right? So in a ramjet engine, you first accelerate the rocket or the missile or whatever it is to a certain, I think, Mach 2 and beyond, at least Mach 1, and then the supersonic ingestion of air powers the secondary motor, which is a ramjet, right? So you can have nuclear power ramjets instead of chemical fuel powered ramjets, and that technology does exist. It's been tested out. You have a reasonably small nuclear reaction going on. It heats air to incredible temperatures, and that's what powers the ramjet. So it is certainly possible to do it. So if you have a nuclear powered ramjet, you could use the same technology on aircraft. So the technology seems to exist, yes, yes. But because of these concerns, nobody wants to have flying nuclear reactors, right? So that's the reason why it's not taking time. It's that it's just a little bit too hazardous. People are already scared of nuclear technology. We have one or two incidents that have happened in the past. The 3 Mile Island incident, Chernobyl was a disaster. Fukushima, unfortunately, it's something that happened in 2011 that was not nice. Yeah, so these things scare people. Nuclear technology is unfortunately associated with the atomic bomb, which is a horrific weapon, and that's why people are scared. And it's politically like in a hot potato kind of thing, using nuclear technology on aircraft and all that stuff. People will be scared. There was this technology called nuclear magnetic resonance imaging, NMR imaging. They had to rebrand it and call it MRI, magnetic resonance imaging. It's the same thing. They've just given it a new name, MRI, instead of NMR, because NMR stood for nuclear magnetic resonance imaging, and that scares the heebie-jeebies out of people. the term nuclear. So there are multiple factors that go behind this, and that's why nobody has taken this, has done this, especially for commercial aircraft. But we do have certain nuclear powered missiles. I believe the Russians announced that they have a nuclear powered cruise missile. I think they announced it in 2019, if I'm not mistaken, 2018 or 2019. So the technology does exist, but for these reasons it's not been adopted widely. Maybe there are some secret projects that are being run by certain countries, nations, yeah, that would be utilizing such technology, but it's not been announced or revealed or made available in the public domain, right? And there's this associated question about nuclear microreactors. Are they a viable and stable alternate power source in resource scarce regions or for long-term operation? So when you talk about nuclear microreactors, I mean, one would imagine a nuclear reactor that can be carried on a car, or something that, well, not something you can carry in a suitcase, most likely. That would be really scary. But yeah, something that can be transported by car, yeah, and installed in homes or in buildings, and that would power the entire building for the foreseeable future, as long as the nuclear fuel lasts. And the fuel obviously would be replaceable, and so on and so forth. It is certainly something that can happen. The only constraint is that, first of all, nuclear fuel is extremely expensive. It's typically uranium. You can also use thorium, you can also use plutonium. These nuclear fuels are extremely expensive, and they have multiple uses. I mean, you put a nuclear reactor into civilian hands, god knows who else will get their hands on it. So it's something that needs extremely tight security, and that's why it's only used for typically for military and other purposes. You can have nuclear reactors that power a city and all, but those nuclear reactors are very heavily guarded, right? There's very strong security, multiple layers of security. So typically it's something you don't want the nuclear fuel essence especially to fall into the wrong hands. It's something that lots of people would love to get their hands on, and all kinds of shady and dodgy people and governments. We don't want that to happen. So that is the primary reason why nuclear microreactors haven't made their way into people's homes and buildings and stuff like that. The technology, if you can miniaturize a nuclear reactor and put it on a nuclear submarine, if you can have a nuclear powered ramjet on a cruise missile, the technology certainly exists to miniaturize it that far and make a micro reactor, right? So I don't see it gaining wide adoption because of the security concerns that go along with this. Yeah, you would, you can make a microreactor and install it in a building, in a house, but you would need 24 by 7 by 365 armed guards and multiple layers of security to safeguard that, and that is something that's going to cost you a lot. Yeah, and the nuclear reactor itself will cost a lot. So it's not financially feasible thus far, as far as where we are in the 21st century. Maybe 100 years down the line, maybe, I don't know, maybe even 20 years down the line, if you can solve the security issues and things like that. Yeah, so it is certainly something that can be done, but the nuclear fuel is very expensive, and there are these security issues. So what we can do is we can have multiple nuclear reactors in a nation, and that can power the nation. I believe France, for instance, gained I think about 70% of its electricity needs are met by nuclear power stations, nuclear reactors. Yeah, so you don't need nuclear micro reactors. You can have massive reactors that output a massive amount of electricity that can power an entire city, an entire state, and maybe a significant percentage of an entire nation's power supply. That can be done. So that's why we go big rather than small. That is the reason why it is so, and that's why I don't see it gaining a lot of currency. Micro reactors, for these reasons. All right, next question. Okay, Saurav says Nick Brown, a renowned researcher in the field of psychology, said that you can't turn science into technology unless the science is solid and repeatable. That is correct. Then how did fields like psychiatry, social studies, behavioral sciences, etc., flourish if behaviors, the very root of all these fields, are still not very understood? See, technology, I totally agree with what Nick Brown, I don't know about him, but if he has said this, he's absolutely right. Technology, science can be turned into technology only if it is very well understood and you can repeat it on demand, right? If you can replicate the phenomenon again and again and again in a reliable manner, in a foolproof manner, on demand, then you can turn science into technology. So you have so many examples of that. Laptops, they build laptops and telecommunications, they are all built on top of quantum technology, and so on and so forth. So we have all these technologies which are reliable and repeatable, right? So science can be turned into technology only when it is that way. Now, I do not consider psychiatry to be a science. It's voodoo. I know some people will get upset. Well, well, that's just what it is. Don't agree with me? That's fine. Feel free to disagree. Social sciences are even less of science than psychiatry. Behavioral sciences, these are not sciences. Just because we put science at the end of social doesn't make it a science. Some people call themselves, I'm a social scientist. What a joke that is. There is no such thing as social science. It's not a science. It's social voodoo. And psychiatry, again, psychiatry is about understanding the human mind, yes. Now, we know, to the best of our understanding, from all these centuries of understanding the human body and the human behavior and all that, we know that the seat of the mind, the seat of consciousness, is the human brain. You can cut off somebody's arm, the person's consciousness will not change. Yeah, people can suffer all kinds of injuries, arms, legs, etc. Their consciousness remains intact. It's only when the brain is injured that there are altered states of consciousness, or if somebody suffers catastrophic brain damage, the consciousness evaporates, disappears, to the best of our knowledge. So the seat of consciousness, the seat of the mind, is the brain. Now, tell me about any any medical discipline. Let's say cardiology. In cardiology, you scan the heart, you take detailed you image the heart through various means. by injecting dyes into the bloodstream. And you can do a CT scan or whatever, right? You can do MRI scans of the heart to see if the heart is not working fine. You can see where there are blockages and all. So you take detailed images of the organ that you are studying and that you're trying to heal. When it comes to various other organs, whether it's bones or whatever, you take detailed, you image the organs you're studying and you're trying to heal. When it comes to psychiatry, do they ever take brain scans? Do they ever look at what's wrong with the brain structurally, physically? No, no, they don't do that. They just infer what may be happening and diagnose things. And that's why psychiatry is such a poor science. I am sure there are a few good psychiatrists who actually do it, take the thing seriously and do it in a scientific manner. Yeah, I know some comments are coming in. That's all right. That's all right. Some people will not like it, but this is my perspective. Psychiatry is not a rigorous science. Psychiatry is still hand waving and voodoo, and that's why most psychiatrists don't really produce any results for their patients. Yeah, patients may feel that something has happened. That's mostly the placebo effect. Yeah, and they prescribe various drugs, chemicals, etc., based on very very vague clusters of symptoms. Psychiatrists typically look for certain clusters of symptoms. Yeah, unfortunately, those clusters of symptoms can be caused by a variety of pathologies. Some could be mental, some could be actually structural. Somebody fell down as a kid when they were 3 years old, they damaged their brain. No one knows that there is brain damage, and that persists and that manifests itself as a certain cluster of symptoms, and so on and so forth. So you need to actually scan the brain first of all. No psychiatrist that I know of does this. Maybe 1% of psychiatrists must be doing it. So they don't even look at the organ they are trying to heal, and then they call themselves medical professionals. It's a joke. Psychiatry, as of today, is mostly a joke. Yeah, it's not a reliable science. Social studies is just voodoo. Yeah, it's I have nothing against studying society, but you have to do it in a scientific manner. You have to do it statistically. You have something called statistical mechanics in physics, where you look at the large scale behavior of gases in thermodynamic systems and things like that. It is a rigorous science. You can apply similar principles to the study of society. You look at it statistically, and you can see how behaviors emerge, how various how things change, how society evolves over time, and you can look at certain parameters, but you have to do it statistically, rigorously, mathematically, scientifically. Social studies today, most of it is about writing god knows what kind of papers based on people's whims and fancies. It's a joke. I do not consider social studies to be a science whatsoever. And behavioral science, once again, it's about looking at various clusters of behaviors and clusters of symptoms and all. It's in a way similar to psychiatry. And yeah, so I do not consider any of these fields to be scientific in nature. And if some people don't like it, well, they can keep coping. Okay, cute whatever. Yeah, I don't know what the name is. Okay, the question is, what's your take on homeopathy? Is it useless? And the doctors are fooling people. Why do so many people claim that they got permanently cured and refer others? Their medicine has a weird way of working. Is it, if it's that highly diluted, why does it smell strong like alcohol? If it's true, it has to be a placebo effect. What's your take on this? Yeah, right. There is something called, there is a term, right, that people use, homeopathic dose, which means a dose that's so dilute that it's insignificant. So listen, homeopathy is something that I believe emerged in the 19th century in Germany, I think. Yeah, and at that time, the field of medicine had not even taken off. We did not even understand where diseases emerged from. Most of them emerged from microorganisms and all that. We did not know that yet. Yeah, so so homeopathy emerged in the 19th century, and it kind of worked for some people, and even today it's still a thing, and there are lots of homeopathic practitioners and so on. So a couple of days ago I had this interesting discussion with Dr. Sid Warrior, who's a neuroscientist. He said that homeopathy actually works for many people, and the way it works is not because of the doses or whatever, but because of the way the doctor interacts with the patient. So typically, when you go to a regular doctor in India, especially when you're paying less, and when you go to a hospital with 5 million patients waiting in line, the doctor will typically speak to you for like 60 seconds or 120 seconds, 2-3 minutes at most. Very brief interaction, and he or she will prescribe whatever they think is right based on whatever symptoms you're exhibiting, and you're done, out. And then the medicine is what we call allopathic medicine, right? In the case of homeopathic doctors, the doctors will take their time in interacting with the patient. They will ask him, how was your day, how are your kids, how's your wife, how are things, how's your work life going, and so on and so forth. They're going to take a good 30 to 45 minutes interacting with the patient, asking very detailed questions, and the patient feels that the doctor cares, you know. So and that is the primary reason why the treatment works, because the patient actually trusts the doctor, and it is the trust that causes that, what you would call a psychosomatic kind of reaction, and that again is a manifestation of the placebo effect. So it's not the medicine that works, it's just the fact that the doctors treat the patient in a certain way, and the patients, because of that, they end up really trusting the doctor. And when you trust a doctor, even if they give you a salt pill and you swallow it, you're gonna feel that it's working. And the fact that you feel it's working is gonna activate certain healing mechanisms in your body. Yeah, the body has the brain can produce certain chemicals that can have pain killing effects, and they can make you feel better and all that, right? So the placebo effect depends on a variety of factors, and it seems that the homeopathic practitioners have cracked the code of how to induce a placebo effect in patients, right? So the medicines don't work. If you it if an allopathic doctor were to prescribe the homeopathic medicines, it's guaranteed that there will be no effect. The medicines won't work. The treatment works only because of the induced placebo effect, the way the doctors interact with that patient, the homeopathic practitioners interact with the patient. So to sum it up, the medicines, whatever the medicines are, whatever the pills or whatever is, they don't work, right? They don't work. It's the it's just that they have figured out how to induce a placebo effect in people, and maybe it works for some people, but it's certainly not going to cure cancer or some genuinely serious illnesses. You got a cough, you got a cold, or you got some long-term chronic problem that can be resolved by placebo effect. Yeah, it's going to work that way. I have no idea why does it smell like alcohol. I've never tried any homeopathic treatment. I don't know what it smells like. I believe it's sugar pills with, I don't know, something infused in them. uh, Typically I've seen those round little pills that people ingest like 7 times a day or 87 times a day. I don't know what is it. So I don't mean to disparage or demean something that does indeed work for some people. Yeah, but it's not the pills that work, it's not the so-called medicines that work. It's the way they interact with the patients that induces a placebo effect, and that's what causes some people to get better. It's not going to make everybody get better. Yeah, you got heart disease, you go to a homeopathic doctor, it's not going to cure you. Please be assured of that. You're going to need treatment from a proper cardiologist. That could actually cure you. You get angiopathy or whatever it is, uh, bypass procedures or whatever, in case you have, I mean, in case somebody has cardiac issues and so on, depending on what your issues are. So that's how it is. So homeopathy is nothing but a way of inducing a placebo effect, and that works for some people who have not very serious conditions. For other people, it's not going to work. So be careful. All right. Next question. Here we are. It's by Swapnil. What's the controversy surrounding the creation of the Darvaza gas crater in Turkmenistan? What chemical reaction has caused it to be still on fire after 50 years of its formation, and will it ever get extinguished? The Darvaza crater. Let's take a look at what this thing looks like. Let me Google that up. Darvaza crater. Darvaza crater. Let me put that on the screen so that you can see what this thing looks like. The Darvaza crater. It's something that's in Turkmenistan. It's a gas crater. Let's see the images, shall we? These are the images of this crater. So it's a crater. It's a hole in the ground essentially that is on fire. It's been on fire since, I think, the 1970s. So yeah, around 50 years, about half a century, and some people have gone into it and so on and so forth. So what's the story behind this? Is there any controversy? Right? So what is this thing? It's in Turkmenistan. In case you don't know where Turkmenistan, let's go to the map. Yeah, let's do that as well. We have maps always. So let's go to Turkmenistan. Where is Turkmenistan? Let's go to the map. Turkmenistan is not far from India, in case you're wondering. It's not really far. It's northwest of Afghanistan, which was once Gandhar. So this here is Turkmenistan, and in here somewhere in this territory of Turkmenistan, you have the Darvaza gas crater. So now let's get that off the map of the screen. And what is this gas crater? So I believe the story. See, Turkmenistan in the 1970s until the early 1990s was part of the USSR, the Union of Soviet Socialist Republics. Yeah, it was part of the Soviet Union, Turkmenistan. Uh, so there are gas resources, natural resources in Turkmenistan, natural gas and petroleum, etc., to a certain extent. So various Soviet geologists were scouring the length and the breadth of the Soviet Union to find more such reservoirs of petrochemicals, of gas, natural gas, and so on. So they were doing some drilling, some excavation work, some investigation work in Turkmenistan, and then they found this big vein of gas that was emitting natural gas, methane, and various. Natural gas is a mix of various gases, combustible gases. And they were actually not looking for natural gas, they were looking for petroleum or something like that. They were looking for oil most likely. So that when they discovered gas, it's not what they wanted. They did not have any use for it. They did not most likely have the means to collect it and use it for commercial purposes and energy generation. So what they did was they decided to burn it off. They thought it's a small pocket of gas or whatever. Yeah, so let's burn it off. It'll burn off in a few days, maybe a week, and then we can move on with our work. They set it on fire. It is believed to be in the 1970s. Yeah, satellite imagery does seem to suggest it began in the 1970s. So they set this thing on fire, and eventually the entire gas pocket collapsed, and it created this big crater, which you can see. Let's put it again on the screen. So there was a dome on it which collapsed, and it gave rise to a big crater, as you can see. So this began in the 1970s. It started burning. They thought it will burn out. The gas will get extinguished, will burn out in a few days, maybe a week, maybe a month maximum, and it's still burning. So that's what happened. It looks like it's a very deep well and very deep reservoir of natural gas, and it's burning, and no one knows when it will be extinguished. Whether it will be possible for it to extinguish itself on its own naturally, or will some human intervention be required? I believe the president of Turkmenistan, Gurbanguly Berdimuhamedov, I think that's his name. Apologies if I got it wrong. So I believe the president of Turkmenistan a few years ago had ordered that this be extinguished or whatever, but clearly thus far it's not happened. Is it possible to extinguish it? So I think the diameter of this thing is about 60 or 70 meters. That's a massive crater. It's not small. It's not a small crater. 60, 70 meters is big. As you can see human beings for scale. It's a reasonably massive crater, and it just keeps on burning. It's not turning off on its own. Now there are other craters like this. There are other examples of fires that keep burning. I believe there is something in Azerbaijan or Armenia. There is some a fire that's been burning for about 4,000 years. I think that's what gave rise to the Zoroastrian tradition of keeping fires burning forever. Zoroastrians worship fire, Agni, right? So I think this gas well in Armenia or Azerbaijan, wherever it is, that could have been the root cause or the origin of this Zoroastrian custom of keeping fires alive, for centuries. So there is one such example somewhere there in the Caucasus region, Turkmenistan, Azerbaijan, Armenia, where you have a fire that's been burning for more than 4,000 years. Then in Australia, there's something called a burning mountain. If I'm not mistaken, let's Google it. Is it Burning Mountain, Australia? Burning Mountain, Straya, Burning Mountain, Straya. So this here is a mountain that inside this mountain there is a coal vein or coal seam or something that has been burning for God knows how long. I don't know, centuries perhaps. So even this thing has been burning for a very long time, maybe more than 1,000 years, and it's a most likely a natural fire. So you have these phenomena that take place. There's even been a natural nuclear reactor somewhere in Africa that existed, that was active more than a billion years ago. So some such phenomena occur naturally, but in the case of the Turkmenistan Darvaza crater, it is something that was created artificially by geologists who assumed, I would say a little naively, that it would burn out in a week's time. There was no evidence that it would stop burning in a week's time. So they made the assumption, the kind of naive assumption, that it's a small pocket of gas, it will burn out on its own. It's still burning, and it may be possible to extinguish it naturally. So fire needs three things: it needs oxygen, it needs fuel, and it needs a heat source. So in the case of the Turkmenistan gas well, the Darwaza gas well, the fuel is there, natural gas, right? Oxygen is there, the atmosphere, which the crater is directly exposed to. And the heat source was provided by the Soviet geologists. So they ignited the fire and it's still burning. So the heat source is there, the fuel is there, and the oxygen is there. So you want to kill the fire, you have to deprive it of one of these three things. The natural gas, there seems to be an apparently inexhaustible reservoir of gas. So you're not going to be able to cut that off. Oxygen out there, that's one thing. Or the fire, the fuel. Now, sorry, the temperature, the fire, the spark. The spark is there. The I would say the easiest way, comparatively easiest way, would be to blanket it in sand or something, which would cut off the access to the oxygen for the flames, and that could maybe stop it. But then you would have all this natural gas escaping into the atmosphere. Maybe they would want to take care of that as well, maybe by sealing the crater. So it's not an easy task to switch off the fire and to seal off the crater and stop the natural gas from escaping. So the question for the government is it worth doing it? It's going to cost a lot of money, manpower to do that. Is it worth doing it, or can we just use the money for something else, the resources? So that's where we are. So there's no real controversy as such. This is what happened, and it's something that keeps on going. And I think it's kind of a tourist attraction of sorts these days. People want to go there and have a photograph there. It's even been used as one of the pit stops for a rally, car rally or whatever, motorcycle rally or something. So yeah, it's become kind of a tourist attraction. It's one of the attractions that you have in this nation of Turkmenistan. People, if they go to Turkmenistan, they want to visit the Darwaza crater. So maybe it's something they may want to keep going, perhaps. So it's for them to decide. So there's no controversy as such. This is what happened. Shazam says, what type of radiation is released by mobile phones? Is it harmful? Good question. So mobile phones, where's mine? It's not here. So mobile phones is something we all carry. We all carry it. Unfortunately, we carry it 24/7 essentially these days. So and the mobile phones do emit certain amounts of radiation, and that's why it's something that is of utmost concern to most people, hopefully, as to what sort of radiation is it giving off. Is it harmful, right? So the radiation we are talking about is electromagnetic radiation, photons. We're talking about photons, electromagnetic radiation. Now electromagnetic radiation occurs in a spectrum, various frequency wavelength. It's two sides of the same coin. So there's a whole spectrum of electromagnetic radiation, and you could crudely, roughly divide it into two parts: ionizing radiation and non-ionizing radiation. So what is ionizing radiation? It is radiation that is so energetic, it can knock electrons out of atoms, it can break chemical bonds, it can damage DNA. That is a scary radiation. That's what we don't want, because you have that next to you. It's going to mess up your internal structure. If it causes DNA damage and mutations, that gives rise to cancers. So ionizing radiation is dangerous. What is ionizing radiation? X-rays, gamma rays, etc. Even ultraviolet radiation, ultraviolet light is to some extent ionizing radiation. Yeah, ultraviolet rays are dangerous. They can cause skin cancer. That's why people with very light skin tones, white skin, the ones who live in Australia, they have a very high incidence of skin cancer, because Australia is a very sunny place. And you have these people who don't belong there, who now have occupied the place. They're living there, the white people. They've got very light skin, and that's something that is unable to ward off the electromagnetic radiation, especially the ultraviolet rays that do make it through the atmosphere. The natives of Australia, they have very dark skins. That's why they are naturally protected. That's how they've evolved over 60, 70,000 years. So yeah, okay. So now coming back to radiation emitted by mobile phones. What what manner of radiation is it? Okay, let me put something on the screen. What is the spectrum of electromagnetic radiation, so that it will give you a good illustration of how it is. Electromagnetic radiation. Let's put that on the screen. Let us see the spectrum. Google search electromagnetic spectrum, and then we do a Wikipedia. We do a dive into Wikipedia. Now, for Wikipedia, let me again remind you all, it's not entirely reliable, but for the sake of, when it comes to science, it's more reliable than as opposed to history. So here, if you can see, we have the electromagnetic spectrum. So we have ionizing radiation, then you have the visible part of the spectrum, and then you have low frequency radiation. So when it comes to visible light, okay, the light that we can perceive with our eyes, that's what we can see, right? It's got a wavelength of between 100 nanometers to 1 millimeter. Yeah. Actually, even not that. Near infrared. So yeah, you can see over here what the visible spectrum is. It's near ultraviolet, from 1 micrometer to 100 nanometers, around that. Yeah. Then you have ionizing radiation that starts from the ultraviolet to the extreme ultraviolet, to soft X-rays, to hard X-rays, to gamma rays. Extremely high frequency and high energy radiation. So you can see how much energy each photon carries. 1.24 MeV, which is gamma rays. That's frightful, right? Extreme ultraviolet radiation. The photons have about 124 electron volts of energy. Even that is scary. Yeah. Now, when it comes to mobile phones, they give off radio waves. The mobile phones work in the radio frequency spectrum. So it's typically a high frequency media. I'm not sure exactly which part of the radio wave frequency it uses, but it's typically not very high frequency. It's maybe high frequency medium or whatever, right? So mobile phones, as far as we know, as far as we are told, the radiation that they release is very small amounts of radio frequency electromagnetic radiation. And mobile phones essentially are radio sets. Yeah, two-way radio sets. So that's what they are. And we need all these cells, mobile cells, these towers which act as transmitting stations. And that's why they're called cell phone, because we need these various cells in a particular geographic region. So as far as we know, from whatever information is available in the public domain, the only radiation that mobile phones release is radio waves. Radio waves are not ionizing radiation, not by a far distance. Radio waves are safe. Okay, so the thing is this: the only way to know for sure is to have radiation detectors. You would need a Geiger counter, GM counter, or something, and detectors of various kinds. You put that next to your mobile phone, and only then will you know for sure. I mean, these counters are not available in the expensive and not readily available. So I have never done a test on my mobile phone with what sort of radiation is it releasing. So what we do is we trust what the authorities say and what the mobile manufacturers say. They say that it's radio frequency radiation, which is not a concern. If it is only that, perfectly good, no issues. And as far as we know, there are no radioactive elements in mobile phones. And if there are no radioactive elements, there should be no ionizing radiation, whether it's extreme ultraviolet or X-rays or gamma rays. So from what I can see, from all the information that I have seen in the public domain, it appears that mobile phones are safe. They only work in the radio frequency electromagnetic spectrum, which is safe, which we know is safe. Yeah, so that's what I can tell you. Okay. Dongar Singh Chauhan says, how is it possible to hear sound from a black hole? Okay, so to answer this question, first of all, we have to address the question of what is sound? How is sound produced? And how do we perceive sound? By what mechanism do we perceive sound? If you understand that, then we'll be able to answer this question. Yeah, so let's unpack a little bit. What is sound? Sound is vibration. Vibration of what? The vibration of the air molecules in the atmosphere. That's what sound is. So I have a sound source. This, the larynx, right? My sound box, voice box, yeah, over here. It's producing the speech that I am currently uh, issuing forth. Yeah, and that is what that does is it produces vibrations, and that these vibrations make the air molecules in this room vibrate vibrate at those frequencies that we perceive as sound. So these air molecules vibrate, hmm, and those vibrations are picked up by our ears. There's this very sensitive structure called the eardrum, and there's a whole structure that connects the eardrum to nerve endings that essentially go back into the brain, and that's how we perceive these vibrations as sound. So our brain interprets these vibrations at various frequencies as sounds of different pitches: high pitch sound, low pitch sound, that sort of thing, right? All right. So that's how it works. So different frequencies produce, we interpret that as different pitches of sound. Now I am speaking in this room in a certain location on the planet. You all may be on different parts of the planet, maybe in opposite sides of the planet, depending on where you are. And you are able to hear me. What's happening? I have this instrument here. It's called the microphone. It interprets these vibrations that I'm producing in terms of, I think, the electromagnetic spectrum, that is then transmitted across the internet, and then it is reinterpreted again back as regular sound through whatever speaker you have, whether it is these tiny little speakers, right? Tiny little speakers or big speakers or whatever. So that's how it happens. So sound is the vibration of a medium. The medium we are in is the Earth's atmosphere, the air molecules that we uh, are immersed in. Sound is the vibration of that, and there's a whole frequency of sound waves as well. Like, just like we have uh, a spectrum, electromagnetic spectrum, there's a sound spectrum as well. We can't hear what is it called, what the bats hear, uh, ultrasound. It's called ultrasound, right? Cats and dogs can hear that, I believe. There are certain whistles that only dogs can hear. You blow it, you won't hear a thing, but dogs will be like, what is that? Here I am. Right? So the human ear can perceive a certain range of frequencies of sound. Now that we kind of understand what sound is, vibration of the air molecules around us, the question is it possible to hear sound from a black hole? Now, black holes are way, way, way far away from here. The closest black hole that we know of is is a supermassive black hole at the center of our galaxy. Hmm? And this is a reasonably passive black hole. It doesn't have an accretion disk, so it's not doing much. Yeah, and it is sitting in vacuum. I think there is an internet issue. Is there? Let me resolve that. Hopefully, the connection is unstable. It says, one second. Please give me a minute. I think there is an issue with the connection. Happens occasionally. Let me take a look at the chat. Are you able to see me well? Is there a lag? Is there a lag? Is it fine? Is the connection good? I think the connection is good now. Okay, thank you very much for the feedback. Let's go back to the question. Okay, so now that we know what sound is the vibration of the air molecules around us. That's what we perceive as sound. A black hole sits in outer space. There is no atmosphere there. There are no air molecules there. It's an almost perfect vacuum. So if a black hole vibrates in some way or whatever, yeah, it would vibrate in the gravitational waves range. Yeah, it will have gravitational frequencies. So there is no air molecules or atmosphere that it is making vibrate. So then how do we hear sound from a black hole? You can't. But what you can do is, when there's a merger, let's say two black holes are merging, they merge together, they're going to make big waves in the fabric of space-time. They're going to create these gravitational waves, massive gravitational waves. See, when you're sitting at the seashore, hopefully you see little small waves, little ripples, yeah, But unfortunately, once in a long time, once in a few decades, you have a tsunami. A tsunami is just a wave, but it's a massive wave. So when you have two black holes merging, they produce a gravitational wave tsunami, a massive wave with a huge amplitude. And that's what our gravitational wave detectors pick up. Now, these gravitational waves have frequencies and wavelengths, just like light has frequencies and wavelength, and just like sound has frequency and wavelength. So, what scientists can do is they can, once they have detected a gravitational wave signal, they can interpret that frequency in terms of sound waves, and they can produce an equivalent sound that is representative of the gravitational wave that was produced by the merger of two black holes. So you can interpret that, extrapolate that into the sound spectrum, and take a look at what it would sound like if it was not gravitational waves but sound waves. That's what you can do. Then you also have certain black holes that are surrounded by these massive, massive gas clouds, accretion disks. In these tightly packed, dense gas clouds, there are molecules of gas. Over there, if you are unlucky enough to be there, you would hear sound if you are in that environment. Yeah. So if you are there, you could actually hear sound. And if you can detect that accretion disk, and for whatever through whatever means you can see at what frequency it's vibrating, you can recreate that sound on Earth, and that would be actual sound. Yeah. So these are some of the ways in which you can possibly hear sound from a black hole. Firstly, you could interpret the gravitational waves it's emitting in terms of auditory sound waves, and that's what that would sound like. Or if it actually has an accretion disk, and that accretion disk is vibrating at a certain frequency, you could recreate that frequency here on our planet, and you could hear what it actually sounds like over there. So these are two possible ways in which you could hear sound from a black hole. You would have to recreate it over here. You cannot directly hear it because it's separated from us by the immense vacuum of space. But you can recreate and reinterpret that sound on Earth, and it would sound like what it sounds like over there to some extent. All right. Okay, Yathartha says, are black holes actually fuzzballs? Fuzzballs. What are fuzzballs? I, you know what I like about this question? The first part of the question is, are black holes actually fuzzballs? And then he asks, what are fuzzballs? That's how you do science. You keep on asking why or what until you get to the root of the matter, right? So first of all, to understand whether black holes are fuzzballs or not, we have to understand what fuzzballs are. Okay, so what are fuzzballs? I think it was Samir Mathur who came up with the term fuzzball, if I'm not mistaken. That's the paper about 15, 20 years ago that he published. Fuzzballs. So what are these fuzzballs? A fuzzball is a bag of strings, or bag, box, ball, a ball, a ball that contains strings, a ball filled with strings. Now you should ask me the question, if you are awake, what are strings? You want to get to the root of the matter, you have to ask that question. What are strings? I am saying a fuzzball is a ball, a bag of strings. So then you need to know what strings are. Strings are one-dimensional uh, vibrating objects made up of pure energy, essentially. You can think of it that way. That's the best analogy I could offer you. One-dimensional uh, objects made of pure energy that are vibrating in various manners. Now you could also ask me what dimensions are. Let's not go as far as deep as that. I'm sure we all understand what dimensions are. Three dimensions of space that we live in: length, breadth, height. Three dimension. This is a three-dimensional object. Yeah, it has length, height and breadth, and so on. And there's a fourth dimension of time which we perceive vaguely, and so on. So these strings are not three-dimensional objects. They're not two-dimensional objects flat. They are one-dimensional objects made of pure energy that vibrates at certain frequencies in complex ways, and that is the building block of string theory. Yeah. So this is one way in which you can actually create a black hole from the inside out. You can build a black hole mathematically from the inside out using one-dimensional strings. You put a bunch of strings together in a ball, and then you calculate the properties this ball has, and you can build a black hole out of that. So how are black holes built mathematically? They typically emerge as the solutions of Einstein's field equations in general relativity. Even before general relativity came out in 1915, the concept of black holes did exist. Yeah, it all starts with the concept of escape velocity. Every object has a certain escape velocity. For Earth, it's what, 11, 12 kilometers per second. One quote me on that, somewhere around that. The Sun has a much higher escape velocity. Jupiter has a much higher escape velocity. So for each gravitating object, you have a certain escape velocity. What if an object is so dense and so large, so dense, that the escape velocity is equal to or greater than the speed of light? In that case, even light cannot escape from that object, and that is the concept of the black hole. So it's something that predates general relativity, but the actual rigorous mathematical singularities emerged out of the equations of general relativity, solutions of Einstein's field equations, which gave us black hole solutions. Singularities are these horrific, scary objects that divide you by zero. All right. Unphysical objects, which actually tells us that there is something deeper at work over here, and there are certain flaws in general relativity which can only be solved by uh, quantizing it, and we still haven't been able to do that. So typically black holes they arise out of the equations of general relativity. General relativity is a large scale theory, macroscopic theory, a theory of the macroscopic world. Now when you're building a black hole in a quantum manner, you have to do it inside out instead of outside in. So how do you build a black hole quantumly? There are multiple ways of doing it. You can model a black hole as a bag of photons. You could do that. It works. It gives you a whole different set of properties than the classical black holes. Yeah, the Schwarzschild radius doesn't work there. There's something called a critical radius, which is different from the Schwarzschild radius, and so on. I'll not go there. So what Samir Mathur, as far as I know, he's the first person. If I'm mistaken, forgive me. But what Samir Mathur did was he created a mathematical black hole out of a collection of strings, and he called this thing a fuzzball. Right. So that's how that's one way of building a black hole inside out at the very small, from the very small scale, using one-dimensional strings. You could use a bag of photons, a bag of gravitons, or whatever. You could do it in a variety of ways. So what this model is the fuzzball model, a bag of strings, and you can uh, solve the mathematical problem. You can work out the equations, and that gives you a black hole. Yeah, and that kind of solves the, not solve, but it's one way of avoiding the singularity problem. The singularity problem is that deep inside the black hole, at the very center, the space-time curvature becomes infinite, and the density of matter also becomes infinite, which is unphysical. Infinities are unphysical. So in the case of the fuzzball model, you have a bag of strings. So there is no singularity within. Interesting, isn't it? So that's what the fuzzball model is. Are black holes fuzzballs? I don't know. Nobody knows. Nobody knows what black holes actually are. We will know only when we have a black hole in our lab, and we can poke and prod it and do various things to it. So we don't have a black hole in the lab. We have objects that appear to be black holes that we have observed. Yeah, supermassive black holes. They could even be wormholes. Who knows? They could even be white holes. Who knows, right? So we don't know for sure what they are, but they do appear to be black holes. They do exhibit all the properties that a black hole would have, but we still don't know what exactly there are. You could create objects mathematically, quantum mechanically, that are not quite black holes but almost black holes, and they would behave almost the same. From a far distance, you could not be able to tell what they are. So the answer is we don't know what black holes actually are, because we know what happens when you are falling towards a black hole. We know there's an event horizon. We know that when you cross the event horizon, you are lost to the universe, more or less. And what happens inside, we don't know. No one knows exactly what is inside. Is there this monstrous singularity? Is there a bag? Is there a bag of strings? Is it a bag of photons? Is it a bag of gravitons? Is it something else? Unicorns and ice cream? We don't know, right? And that's what the research is all about. That's what we are trying to investigate. What actually are black holes? What would be inside a black hole, right? And to do that, to actually figure out eventually what is inside a black hole, we will have to crack the puzzle of quantum gravity. We will have to reconcile Einstein's general relativity with quantum mechanics and quantum field theory. It's not been possible to do that thus far. People have tried. That's why string theory was devised as a possible solution, but it has its own set of problems. It doesn't seem to be giving us the answers, so we still don't know what's going on. So that's what a fuzzball is. That's what the fuzzball model is. And we still don't know what actually black holes consist of. What's inside a black hole? So the answer is I don't know. No one knows. No, you ask any physicist, they will say we don't know. But we have these different approaches. We have these different possibilities, different models. But which of these works? Which of these is the correct model? We still don't know as of 2022. That's where we are. But good question. Very interesting and fascinating topic. Lakshya Sharma says, could this mysterious dark matter just be primordial black holes all along? Primordial black holes. So what are okay, first of all, what's dark matter? The universe has a certain amount of mass. We observe the universe through our eyes, through telescopes, through various instruments, etc. And we see all these stars, and we see galaxies, and we see gas clouds and dust clouds and nebulae and things like that. Every single goddamn thing we see in the universe is less than 5% of the actual mass of the universe. 95% of the mass of the universe roughly is dark. We don't know what it is. Everything we see is less than 5% of the universe. That's how little we know about the universe. So 95% is unknown to us. Out of this 95%, roughly 25%, very roughly 25% is dark matter, which we have some idea what properties it has and all that, and the rest is dark energy, which we have no clue about. Dark energy seems to be some kind of force or some kind of fluid that permeates the universe. It's here right now, yeah, but we don't know what it is, and it seems to be an anti-gravity kind of force. It's making the universe expand. And the expansion of the universe is accelerating. So it's actually making space-time itself expand. Yeah, that's what dark energy is. Dark matter is this missing matter, this dark matter that we know it exists. It makes galaxies rotate in a certain way, which is counter to what they would rotate like if it was only the visible matter, right? So typically most galaxies have a dark matter halo, a spherical dark matter halo. A typical galaxy is a disk, yeah, like the Milky Way, like the Andromeda galaxy. It's enveloped in a massive dark matter halo, which is actually about 90% of the galaxy's mass. Typically, a galaxy, whatever you see, all the luminous matter, stars, all that, is about 10% of the galaxy's mass. And about 90% is a dark matter halo, typically, on average, roughly. Yeah. So that's what dark matter is. Now, the question is, what is dark matter? What is it composed of? What we know is that it doesn't interact electromagnetically, which means we can't see it. It's invisible. It's not dark, it's invisible. So it doesn't interact electromagnetically. It has no electromagnetic interaction. Most likely, it only interacts through the gravitational force. So it is some kind of exotic matter, because it's not something we experience in day-to-day life. There is most likely dark matter passing through the Earth. The solar system may be enveloped in dark matter. There could be a wind of dark matter particles passing through me right now. Yeah. And we will not know about it. So it is some mysterious matter, a mysterious particle or a mysterious class of particles that all seem to have this common property that they interact only gravitationally. Some people tried to postulate that there could be weak interaction as well, the weak nuclear, the weak force, and that's where the axion came from and all that. But and then various other things as well. It's not quite worked out. So the most likely hypothesis is cold dark matter made up of purely gravitating particles. So what are these gravitating particles? We still don't know. So could it be primordial black holes? Now let's ask ourselves, what are these primordial black holes? When we think of black holes, we think of these monstrous objects at the center of galaxies that are sucking everything in. Yeah. But black holes aren't that nasty or evil. Typically, they're just gravitating objects, purely gravitating objects. Now, they could have charge also and magnetic fields, but yeah. So what are primordial black holes? So in the very, very, very incredibly very early universe, we know the Big Bang model. Yeah, at the very beginning of space of time, All the mass and energy and everything that we see in the universe and everything we don't see was concentrated in a single point, an infinitesimally dense and hot point. And then something made that expand. That is the expansion of space-time, and that's what we call the Big Bang. It was not an explosion, it was an expansion of space-time and everything contained within it. So in the very early universe, you could have had these quantum fluctuations that arise out of Heisenberg's uncertainty principle, quantum field theory, yeah, all that. So these quantum fluctuations happen. We know they exist. They happen everywhere. Empty space, the vacuum of space is not empty. It's teeming with this virtual particle-antiparticle pairs. Quantum fluctuations. So in the very early universe, quantum fluctuations could have produced regions of over densities that could have been the seeds of black holes, very tiny microscopic black holes, primordial black holes, in the primordial very early universe. And there could have been uh, an a massive amount of primordial black holes produced at different early epochs in the universe's history. Preheating, reheating, even pre-inflation, maybe post-inflation. Also, yeah, there are various mechanisms through which there could have been an overproduction of primordial black holes. So most likely, primordial black holes were produced in enormous, abundant quantities in the very early universe. Small, microscopic black holes. Yes. The question is, where are they? Where are they? Now, we know that black holes have a temperature. They're thermodynamic objects. If you have a temperature, you're going to give off radiation. And the smaller a black hole is, the hotter it is. The bigger it is, the colder it is. So supermassive black holes are very cold. Very, very, very cold. They could be colder than the temperature of space, the cosmic microwave background radiation temperature. But the smaller a black hole is, the hotter it is. And the hotter it is, the faster it essentially gives off radiation, the faster it evaporates. And the end point of a black hole's life is a massive explosion. Boom. That's how it goes. That's how it dies. Yeah. So if primordial black holes were produced in enormous quantities in the early universe and they were very small, they could have possibly all exploded and died out, evaporated out. That's one scenario. The other scenario is that by some unknown mechanism, they still survive until today. Maybe they leave Planck scale remnants, the so-called Planckons, cornucopions, whatever they call them these days, Planck scale objects. And maybe at the Planck scale, there is no more evaporation of black holes, in which case you could have a massive quantity of Planck scale black holes that are wandering around, and maybe they make up what we call dark matter. Maybe through some mechanism we don't understand, primordial black holes or micro black holes could have formed bound states, quantum bound states, and maybe in these quantum bound states they don't evaporate. And maybe these quantum bound states don't behave like black holes, but they behave like exactly like cold dark matter, supermassive, not supermassive dark matter, but the cold dark matter, heavy particles. There are all these possibilities. These particles would be quite massive, but very, very, very small. And this is a theory that I had co-authored in 2002, all the way back in 2002. Stable bound states of primordial black holes that could constitute dark matter. So these are all possibilities. There's no way as of today of proving it. If there are bound states of primordial black holes that are stable, and they do exist, they would give off gravitational radiation. They would give off gravitational waves, quantized gravitational radiation. But these gravitational waves that they emit are not detectable with the detectors that we have today. The only gravitational wave detectors that work today are the LIGO detectors, right? The LIGO detectors can only detect gravitational wave tsunamis, enormous gravitational waves, not tiny ripples in space-time. For that, you need extraordinarily sensitive detectors, which you don't have today. So, if primordial black holes did form bound states and quantized bound states, those quantized bound states would give off quantized gravitational radiation, just like you see light, that sort of thing, in those frequencies, in similar frequencies, but in the gravitational wave domain. Yeah. But as of today, there's no way of proving it. So it's just a theory. So it is possible. Yes, it is possible that primordial black holes could be dark matter, or bound states of primordial black holes could be dark matter, or Planck scale remnants of primordial black holes could be dark matter. I would say it's a very high possibility, a strong possibility. Now, physicists have been looking for all kinds of different dark matter candidates. There used to be machos, there used to be wimps. They were looking for they were looking for gravitational wave microlensing, the macho thing, yeah. Massive compact halo objects, machos. They were looking for axions. They were looking for supersymmetric dark matter. All of these searches have turned up empty-handed. Maybe it's time to take primordial black holes a little more seriously again. So it's an ongoing process. But yes, I personally think primordial black holes are a very important candidate for dark matter. Okay, Dr. Nishchay says, why do Asian elephants have smaller tusks or no tusks compared to their African counterparts? I believe that Asian elephants are even physically somewhat smaller than their African counterparts. African elephants typically, I believe, grow larger, somewhat larger than Asian elephants. And I believe even the African lions are somewhat physically larger than Asiatic lions. And the only Asian lions left are in India, Western India, Gujarat, the Gir forest region. Yeah. So why is it so? Well, they have evolved differently. They've evolved differently. Uh, Africa and Asia were connected. Let's take a look at the map. Obviously, let's it makes sense to look at the map since we are talking about these things. Where is our map? So here's the map. So Africa and Asia were connected in this region, the Sinai Peninsula, the Egypt, uh, Egypt, and this region. It's connected. So in the past, animals could have migrated around this place. You had the so-called Barbary lion that lived on both sides of the divide. Now you have this artificial divide called the Suez Canal. It's an artificial thing. It's not a natural thing. So there used to be this land connection here. In the past, during the ice ages, etc., it would have been possible to cross over through the Bab al Mandeb Strait and various other places as well. So there have been connections between Africa and Asia. So it's possible that species transmigrated, etc. But so we have certain species that are present on both continents. Lions are a good example. Elephants are another good example. Now, what we don't realize is how large Africa is. Let's see Africa Asia comparison. Africa Asia size comparison. Let's take a look at that. Let me put this off the screen and let's put something else on the screen. Africa Asia size comparison. Now, why am I comparing sizes? Because it's relevant. See how large Africa is. See where India fits into Africa. Can you see? This is India, this is China, this is the UK, as big as Madagascar, the US. Africa is enormous, and the maps that we use, the mercator projection, they don't show us how large Africa actually is. Africa is a massive, massive place. It's the biggest continent of all. So when you have animals that live in a continent of this scale, they have massive amounts of territory that they can use as their home range. Yeah, massive territories. So they will cover massive distances in various migrations, and that has an effect over the millennia on the size of an animal. An animal that has access to more land and more resources, that sort of animal can evolve, can afford evolutionary, from an evolutionary standpoint, to grow larger, because there is an abundance of territory it can cover and an abundance of food that it has. Africa's grasslands, savannas, etc., are abundant in food, in grassland and all that. So in today we have very few wild animals left in Africa. Even in the 1960s, 1970s, you had so many more wild animals: zebras, gazelles, elephants. It's all been killed off by the white people, by the Europeans, who used Africa as a place for their hunting activities and just killing animals for sport. And just wanton massacres, pointless massacres of animals. That's why the numbers have come down so badly. There are very few animals left in Africa today. Africa was this enormous continent filled with herds, incredibly large herds of animals. Yeah. And it could support so many animals. That's how rich Africa has been. So these animals, they had access to such an incredible abundance of resources. That's why they typically grew larger. That's why the African lions are typically larger than Asiatic lions, and that's why African elephants have over the millennia, thousands of years, tens of thousands of years, evolved differently from their counterparts, their cousins who live in Asia. In Asia, the terrain is different from that of Africa. Asia is full of these river valleys. Like, let's take a look at the Indian subcontinent. There are mountain ranges, the Aravalis, the Sahyadris, the Vindhyas, the Himalayas, etc., the Western Ghats, and so on and so forth. You have that, and you have forest. Today we don't have forests. In the past, you had these massive forests and river valleys. In Africa, you do not have forests. You had these savannas, grasslands. Yeah, so that's why the terrain in the living environment is different in Asia compared to Africa, and that's why it has caused these species to evolve in different ways when it comes to Asia and Africa. So because of that, the African elephants typically grew larger and they had longer tusks. When you grow larger, your tusks also become longer. That's typically how evolution goes. You adapt based on your environment. So that's why Asian elephants are smaller and they have smaller tusks compared to their African counterparts. Okay, Swapnil says, is it possible to print bones using a three-dimensional 3D printer to replace bones that have been broken or damaged beyond repair in a human or animal body? Yes, 3D printing technology is really coming up. It's something that is possibly poised to transform the way we do things. Yeah, the way we construct things, the way we build things. Maybe it's something that could transform medicine as well. So when someone's bone is broken, when someone shatters their femur or tibia or radius or ulna or whatever, if the break is very clean, you can just set the bone again and immobilize it for like a few months, 3 months or so, 3 4 months, whatever, depending on the person. You take calcium tablets and it heals, in a few months. But if the break is complex, if the bone is shattered into pieces or something, then typically what you do is you insert a metal rod, a steel rod, a sterile steel rod, and you reconstruct the bone. You may piece it together using screws. Yeah, that's what's done, and that's typically what's been done thus far. uh, and you have to make sure that the materials you use are sterile and they are non-reactive biologically, right? So typically, if people have used stainless steel, sterile stainless steel, well treated. They have used there's also been the use of ceramics. So ceramics are also very non-reactive. And they are well suited for this sort of uh, purpose. So in the future, yes, it's certainly possible that 3D printed bones could be used. So someone, let's say they've shattered some bone, you could remove those shattered pieces and insert an exact replica of how the bone used to be, but 3D printed. So it's certainly going to be possible. I'm even hearing that you could have 3D printed organs in the future. Yeah, I think that's still some time off. That's still a few years off, maybe a couple of decades off, perhaps. But yes, we are witnessing these advances in medical technology. So the question is, what sort of material is going to be used to 3D print the bones? Um, I would say it should be something that's similar to the bone, to what constitutes a bone itself. See, bones are um, complex things. A bone is not just a solid object; it is porous. You know, it is biologically active. It is alive. Inside a bone, there is this hollow space in which you have bone marrow. Bone marrow is what generates our red blood cells in our blood. Yeah, so the bone marrow is very important. So, um, so if you replace a damaged or destroyed bone with a 3D printed bone, obviously you will not be able to recreate that. But one would expect that you would use calcium based material that would, in a way, recreate what the material or composition of the original bone was like. So I think it's going to be possible. I don't think it's been done thus far, but I don't think it's too far away. So yes, in the future you will certainly have these things happening. More and more materials, including biological materials and bones, will be 3D printed, and that could certainly be the future of medicine. Yeah, so I think it's going to happen soon enough. It's if it's not already been done. Okay, Harsh says, is human extinction possible? If no, then why? If it is possible, then by which way? Virus outbreak, AI takeover, human calamities, natural calamities, human wars, space problem. Um, See, if you look at any species, if you see, our planet is about 4.5 billion years old, and there have been various mass extinctions on the planet. The most recent one was the what's it called? The Chicxulub event, right? The Chicxulub impact, which was something that happened 66 million years ago, in which most of the dinosaurs died out. All the non-avian dinosaurs died out. Um, and various species over time have gone extinct. But some survive, we survive, and our ancestors date back to the very beginning of the planet. So life is believed to have emerged. The unambiguous evidence is that life emerged on our planet about 3.77 billion years before today. Yeah, those were very primitive microorganisms as far as we know, and then over time more complex biology emerged, evolved. You had microorganisms, unicellular organisms in the beginning, then you had different kinds of biology, then you had multicellular organisms, and then more complex life forms emerged. Then you had various marine life, of a whole variety of marine life, and eventually these some of these marine life forms emerged out on to land. They developed the ability to breathe the atmosphere and use that for staying alive, and that's how you had ground based life forms, and we are an example of that. So our ancestors would most likely date back to the very beginning, 3.77 billion years ago. Um, and we carry DNA, which which most likely dates back to the beginning of life on our planet. So we have survived. So our survival, some people would say that Homo sapiens is about 300,000 years old only. Well, Homo sapiens had predecessors and ancestors, right? Archaic humans, and those archaic humans had older ancestors, which were the first apes around 20 million years before today. And those apes had ancestors, the mammal like creatures that survived the Chicxulub impact 66 million years ago. Those little rat like creatures, those rat like creatures had ancestors that were the fish that lived in the marine environment of the planet billions of years ago. Those fish had unicellular ancestors. So we have survived close to 4 billion years. Yeah. So we are a very hardy species. It's very hard to kill us off. We have survived all kinds of mass extinctions. Yes, we have. But of course, human extinction is possible. And we have made it actually quite quite possible to destroy everything off. Um, if two nations go to war and they are both nuclear powers, who knows what could happen? It could kill off most of humanity. Uh, you could have environmental catastrophes, human created environmental catastrophes. If we destroy all our forests, animals will die off. If animals die off, then you're going to have a whole change in the in the ecosystem environment. We could lose our food sources, even our plant sources of food, and that could kill us off. That could cause mass famines and starvation and whatnot, and very few humans could survive. Maybe all humans could die off. If there is a Chicxulub like kind of event, a comet or asteroid that impacts the earth, and we are not able to prevent that from happening, that could most likely kill us off. So lots of scenarios are possible. Virus outbreak, yeah, you could have a pandemic of some kind, an epidemic of some kind. We have had such things in the past. In the past, more than half of Europe's population was decimated by the Black Death, the plague, which kind of skipped India for some reasons, but it ruined the rest of the world. So yes, you could have viruses, you could have pandemics, natural or not. You could have wars. Nuclear war is a great way of killing off everything on the planet. Not everything. Life will survive, but we could end up becoming extinct. Space problem, like you're mentioning, is the impact of an asteroid or comet, which will certainly happen in the future. It could happen in the next 50 million years. It could happen next week. We don't know. Yeah. uh, I think NASA keeps an eye on on all the near Earth objects, especially objects of particular concern, which kind of tend to cross Earth's orbit around the sun, intersect with it. Thus far, there is no immediate cause of concern when it comes to these objects. But yeah, there could be objects that we are not aware of. It just takes one to kill you off. So yes, and AI takeover. That's also a non-zero possibility, a non-zero probability of that happening. So it doesn't necessarily have to be a fully conscious sentient AI. It could be just a non-sentient AI that can still take over the world and possibly kill off humanity. It is possible. So I think there are multiple ways in which humanity can or could become extinct, and we need to all work together and ensure these things don't happen. Yeah. So it is certainly possible. It is certainly possible. It's always been possible in the past. It's even more possible because of our own doing today. And for that, we need good leadership, and we need to take humanity in the right direction. Right now, things are not going well. We are damaging the environment. We are destroying the oceans. If it continues like this, the oceans will be choked with plastic. You could have mass extinctions of fish. There's already overfishing that's happening on a routine basis. So yeah, this is not good. We keep on going this way, it can lead to a catastrophe. So yeah, it's gonna take some good leadership in the future for us to keep going in the right direction. So I think human extinction is certainly possible in a in a multiplicity of ways, and hopefully we ensure it doesn't happen. Jav Live says, why are there no flying cars? Yes, why are there no flying cars? I would like to have one. I will pay whatever it takes. If I don't have money, I will borrow money. I would love to have a flying car, but the fact is we don't have flying cars. Why is it so? We do have certain drone kind of things, like human carrying drone. Do we have a human carrying drone? Let's see if that is possible. Let me put that on the screen. Where's the screen? Here's the screen. Here we are. So we have these drone vehicles that can carry humans. We even have that surfboard kind of thing that takes you in the air. I'm not sure what it's called, windboarding or whatever. So you have these vehicles that are essentially like drones, but drones that can carry a human being, enough for one person. You can even have multiple people in there. So this is essentially a flying car. We already have it. So, but why has it not been adopted widely? Now the technology exists, but it's not adopted widely yet. Why is it so? Think about it like this. Let's say a teenager is given a flying car. Now, teenagers are kind of not very mature people with good reason, because they still don't have enough experience of the world. And teenagers like to party, do various things, alcohol and stuff. Let's say you have a teenager who is drunk in a flying car. What could happen? When you have road vehicles, they are essentially traveling on a two-dimensional surface. Yes, they can go back and forth, east or west, that sort of thing. They are traveling on a flat surface, and they are traveling on pre-designated roads. So if there is any collision, any accident, it will only happen in that particular place. When you give them access to three-dimensional space, which means they can also go on up and down, then it's almost impossible to regulate their behavior. They could go in any direction. They could crash into any building. That's way more hazardous. And then they could even crash into airplanes and things like that. So these are the reasons why it's not really taken off. This technology, the technology already exists. It may be expensive. These flying cars may cost, I don't know, $10,000, maybe $100,000. I'm not sure how much it will cost. I'm sure people can afford it, but there will be a huge amount of regulation. There's already a lot of regulation on these small drones. There are various people who use drones for videography and photography. They when someone is when someone is taking a video of a wedding, you typically have a drone shot, yeah, all the people celebrating from the sky. Then you have various filmmakers who use drones, various YouTubers who use drones to give a cinematic imagery and all that. But we're already witnessing a significant amount of regulation on who can acquire drones and in what way they can use them. They need all kinds of permissions, they need a license. There are certain places where you're not allowed to use your drone, and every time you have a drone flight, you need to first take permission from the authorities that on so and so date in so and so place location I will have a drone flight for so and so duration, it will go this high, and so on and so forth. It is important that this is done, otherwise you're going to have drones flying everywhere, crashing into all kinds of things, taking down airplanes, commercial airplanes and whatnot. It's dangerous. And the same thing applies to flying cars. Once you start allowing people to fly around, it's going to be chaos. It's going to be chaos. So that's why I don't see it taking off to a significant extent anytime in the future, because it's dangerous and many people are irresponsible. You can be irresponsible on a two-dimensional surface. When you are irresponsible in three dimensions, the damage you can do is much more massive. Yeah. So these are the reasons why thus far it's not taken off. In the future, there could be some people allowed to use these drones and flying cars, but again, it will be very, very strictly and strongly regulated with good reason. So that's why we don't have flying cars thus far. Swarup Vaidya says, India is going to launch a $1 billion quantum mission to expand India's capabilities in quantum computing. National Research Foundation NRF scheme will be ready in 6 months, which will take care of the funding of universities and research centers. Your views on this? It is good, it is great, it's very encouraging that the government is investing money in quantum computing. We need to get involved in this. India cannot afford to be left behind in the quantum computing race, in any other race, any technological race. It's very good. It's very encouraging that we are spending $1 billion, which is not a small amount of money. It's good. The question is, how is the money going to be used? That's always the question. I can throw money at something, but how is the money going to be used? That's always the real problem. Now, India's universities, you're going to fund them. Is there any research happening in India's universities? Do India's universities have the research capabilities? Maybe this money will be used to develop the capability to do research. The other question is, do India's academicians have the ability to do research? To answer the question, you have to see how people are given jobs and how they are promoted. In India's universities, you unfortunately have the reservation system, which means it is not a merit-based system. You look at India's professors, academicians, 95% of them are not capable of doing research. They have no inclination or interest in doing research. We know that. There are some good scientists, no doubt. There are some really good scientists as well, maybe 1%, no doubt. But 95% of them are unfortunately mediocrities. They're not capable of doing research. They don't have the understanding of what research is. How will they take India forward in this? What I hope happens is that we set up new institutions where this research is done. Not the good old universities that have been around for 3,000 years. Not 3,000, sorry. All of India's universities are the old ones. I will not name any, but these are colonial institutions. They are run in the same old colonial bureaucratic fashion. The money, the budget is always controlled by the bureaucrats, by the non-teaching staff. And the teaching staff itself doesn't have any inclination for doing research. How much research is coming out of India? Answer me. How much research has come out? How much genuine, valuable, path-breaking research has come out of India in the past 20 years in the field of the sciences? Give me some examples. Can you come up with anything? That's the problem. That's a problem. There are good scientists, some good scientists, no doubt, but they are shackled by the system. So you throw money at you invest money in these universities. I wonder where the money will be used. You go to certain very, very high-ranking institutions in this country, in India, you will find that the labs have 20, 30-year-old equipment, but the conference rooms and the washrooms have millions of dollars invested in them. That's what you find. That's what happens when bureaucrats take decisions and they decide where to put money. Yeah. So that is the problem. So you have the same system that's going on. You put more money into the same system, you will get more of the same results. You understand? So what India needs is, first of all, we need to reform the education system. The universities must be made more research oriented, and promotions and hiring should be done based on merit only, not based on quotas and reservations and affirmative action and God knows what else. That's how you take the country backwards, not forwards. Look at how Germany transformed itself in the late 19th century. It became a technological and scientific superpower almost overnight. They had these universities based purely on merit. Huge amounts of money were invested in real research, cutting edge research. And the scientists were hired based on their capabilities, their ability, and the merit, and they were promoted based on merit. All the various German scientists who were at the forefront of the quantum revolution, they became full professors when they were in their 20s. Some of them became heads of department or heads of institutions in their early 30s. Lots of names, Heisenberg, Schrödinger, Einstein, so many more. Born. Even other countries like Niels Bohr, Sweden. Sweden was it? Sweden, most likely. And so on. There's so many. That's how you take a nation forward, scientifically and technologically. You have the same old corrupt colonial system. You can pour in $100 billion, it's going to produce the same results. So that's the problem. So if India is spending $1 billion in quantum computing, I hope we create new institutes that are purely research based, and where they will hire people based on their ability, not based on quotas. And the only way the money is used will be in doing research, not in the salaries of non-teaching staff and bureaucrats and $1 million washrooms and the $1 trillion conference rooms. Not that. That's a complete waste of money. Look at DRDO. DRDO has roughly 30,000 employees. Out of those 30,000 employees, about 5,000 are scientists. 25,000 employees are non-scientists, non-scientific staff. What kind of a joke is this? This is how the nation's money is being wasted. So it's a good thing the government wants to invest $1 billion in quantum computing. The question is, how is the money going to be used? And that's where I have a few questions. Just saying it. All right. Okay, the question is, Captain Burp 91. What is thrust vectoring, which is used in modern day fighter jets like Sukhoi Su-30 MKI, Lockheed Martin F-22, Raptor, and how does a radar on a S-400 detect stealth jets, but a conventional radar cannot? Thank you. Okay, what is thrust vectoring? It's very simple. See, let me show you what Mach diamonds are. Mach diamonds. Okay, there's something called Mach diamonds. This is the exhaust of jet engine. Shock diamonds, Mach diamonds, call it whatever you want. So typically you have a jet engine that has an exhaust that goes in the opposite direction of which the jet engine itself goes, right? Now, in thrust vectoring, what you can do is you can control the direction in which the exhaust goes. So let me show you thrust vectoring. Thrust vectoring. So it's a technology. You see this? You can send the jet in. If you have two engines, you can make the exhaust of the two engines go in different directions. And using that, you get more control on the way the jet, on the way the fighter plane can be maneuvered. So thrust vectoring fighter planes, which have the thrust vectoring capabilities, are more maneuverable than a jet plane that does not have the thrust vectoring ability. So what the technology does is that it allows you to direct the exhaust in any direction in three dimensions. So that gives you essentially hyper maneuverability. Can you see? You can send the exhaust in any direction you want. So that essentially is thrust vectoring. Like you said, the Sukhoi 30 fighter plane, the Lockheed Martin F-22 fighter plane, and various other fighter planes have this capability. That's what thrust vectoring is. Now, how does a radar on the S-400 system detect stealth jets, but a conventional radar cannot? Actually, all radars can detect stealth jets. The question is, at what range? That's the only question. A good, powerful radar is one that can detect a stealth jet at a large distance. A mediocre radar may be able to detect it only at 10-kilometer range, at which you can't do anything. Yeah, because a stealth jet typically flies. Let's say you're talking about the F-35, which is a reasonably stealthy jet. It's it can fly supersonic. So if you can detect that plane with your radar at only 10 kilometers distance, it's going to be gone in an eye blink of time, and then again you cannot track it. So a good radar is one that can detect a stealth jet at a longer distance, at a greater distance. So I think the S-400 radar, if I am not mistaken, can detect a stealth jet like a typical stealth jet at about 40-50 kilometers distance, right? So that's not a very big distance. A plane can traverse that distance very quickly, but what it can do is it can lock onto the plane. And so the S-400 radar is the AESA radar, active electronically scanned whatever radar, which is a very difficult technology to master. So S-400, the system, it has multiple radars. It has a network of radars that all feed into a three-dimensional battle space environment. That's what they create. And even the missiles have radars of their own. So what the system does, it uses inputs from multiple radar systems to paint a unified picture of the airspace. And these are all AESA radars, which can detect stealth jets at about 40-50 kilometers distance. So they use this to track the aircraft. So it's able to track it. It launches a missile, and it keeps on talking to the missile until the missile is at a range where its own radar can detect the stealth jet. Then the missile is left to go on its own autonomously. So that's typically how it works. So all radars can actually detect stealth jets. The only thing is the distance good enough? You want to detect the stealth jet as far away from you as possible, so that you have the maximum possible reaction time and decision making time. If you are able to detect it only for 3 seconds, you can't do much with that. If you can detect it for like 30 seconds, you can do something with that. So that's how it is. So I think the S-400 radar is good, and it's able to detect stealth jets, I think, around 30, 40, 50 kilometers distance, which gives it a reasonable amount of time to do some damage. Yeah. So yeah, that's how it works. Radar technology. Tech Curiosity says, "Who do you think that the internet is the greatest and most influential invention until date?" It's certainly one of the most powerful and most influential inventions. It's brought the whole world together. The internet became reasonably well adopted, I think, in the late 1990s. People were using it in the mid 90s, but we had the dot-com bubble that in Silicon Valley in the late 90s. Then there was a dot-com crash, and then things went in a different direction, and the internet started becoming adopted for financial transactions, for banking and other things. That's when it was taken seriously, and now it's used for almost everything. You cannot imagine life without the internet today. So it is certainly it's most likely the most influential invention, and it started as a means of making computers talk to each other over large distances. Once that happened, I think it started with ARPANET in the US. Maybe it was first tried out in CERN in Geneva, in Switzerland, possibly. I'm not sure. I don't remember the exact history. But it started as a means of making computers talk to each other remotely over long distances. Once that was feasible, then they started creating networks of computers who would talk to each other, and through this network, you could share documents and data. And over time, Then what happened is that browsers appeared, internet browsers, through which you could which you could browse web pages coded in HTML. Then you had CSS, then you had JavaScript, and things were built on top of each other. So it started as a very bare bones thing, and slowly various technologies were built on top of that, layers and layers and layers of technology. Now you have search engine, you have entire computational engines and whatnot, algorithms. Some people say the internet could have a mind of its own. Who knows? Yeah. So yeah, I think it's one of the, if not the most powerful and influential invention we have ever seen. It's completely transformed uh, humanity. Yeah, the human experience, human existence. So yeah, most likely the most powerful, the greatest, most influential invention till date. Okay, Ayush says, what are gravitons? Are they real? Uh, Gravitons. Okay, so let's talk about the forces. We know of four forces in nature, four forces of nature. Uh, the weak nuclear force, the strong nuclear force, the electromagnetic force, and the gravitational force. We have these four forces. Now, if you look at the standard model, we have what's called exchange particles. What are exchange particles? These are particles that are exchanged, and the exchange of these particles produces what we perceive as these forces. Uh, Mediator particles, exchange particles. So the exchange particle, when it comes to the strong nuclear force, is the gluon. The gluon. Um, then the exchange particle for the weak nuclear force is the W and the Z bosons. Yeah. The exchange particle for the electromagnetic force is the photon. Photons are exchanged. Virtual photons, keeping within the parameters of the Heisenberg uncertainty principle. We have the exchange of virtual particles, virtual photons. It is this exchange of virtual photons that gives rise to what we perceive as electromagnetism. Yeah. So we have electromagnetic attraction, repulsion, depending on the charges and all that, and you have the exchange of photons that produces this force. Similarly, we have the force of gravity. Now, it is hypothesized or theorized that there is an exchange particle that mediates gravity as well, which is the hypothetical graviton. Yeah. So that's the fourth uh, exchange particle that is hypothesized. It's never been detected, it's never been uh, found, but it is hypothesized, postulated, theorized to exist, and that could be behind the force of gravity. In case gravity is a quantum force, in case gravity is a force at all, from the perspective of general relativity, gravity is not a force. It is simply the warping, the bending of space-time. It is the bending of space-time that we perceive as gravity. Yeah. It is the bending and warping of space-time that gives rise to what we feel is the force of gravity. Now, we know that gravity is extremely weak. It is the weakest of the forces. How do we know this? How do we know this? Take a small magnet, the kind of magnet you put in a fridge. Yeah. That small magnet can pick up a paper clip. Yes, it can pick up a paper clip. Do you understand what's happening? The magnet, it works. The force that a magnet uses, it is the electromagnetic force, right? So this little magnet is able to pick up a paper clip and take it upwards. By doing that, it is defeating the force of gravity. Now the magnet is this small. A magnet of this size is able to defeat the force, the gravitational force exerted by an entire planet, the Earth. So a tiny magnet it produces an electromagnetic force that is stronger than the gravitational force produced by the entire planet Earth. That illustrates how weak a force gravity is. Right? So the graviton is going to be incredibly hard to detect. You would need a planet-sized detector. Even that would not work well. Even if you had a Jupiter-sized detector, gravitational detector, even then it may be difficult to detect gravitons. So gravitons are theoretical particles, but detecting them is going to be it's going to be something we leave to our descendants. It's not going to happen within our lifetimes at all. Nobody is going to even try, most likely. to detect gravitons. Yeah, but that's what gravitons are. Are they real? We still don't know. If the general relativity picture is correct, then gravity may not be a quantum force. It may not be a force at all. It may just be an illusion that seems to be a force. It may just be the bending, the warping of space time. But if there is a quantum theory of gravity, if gravity does emerge from the quantum level, from the quantum scale, then you may have gravitons. So we still don't know. But yes, it is a hypothesized, a theorized particle. If you look at any illustration schematic of the standard model particle zoo, you will see the graviton there. Let's take a look at the standard model particles. Okay, let's put that on the screen. Standard model of particle physics. Do we have the graviton in there? They have not included the graviton as far as I can see. But yeah, in some cases people do include the graviton. So yeah, it's something that's not been detected yet thus far, and that's why in some cases you do include the graviton, in some cases you do not, and so on. So yeah, that's the answer. That's what gravitons are. Are they real? We still don't know. Maybe we'll know in the future someday. Okay, what is the temperature of space? The temperature of space is 2 point something degrees Kelvin, which is the temperature of the electromagnetic radiation that permeates space. And what is that electromagnetic radiation? It is the cosmic microwave background radiation. What is that? It is the afterglow of the Big Bang. Essentially, that's what it is. It is the remnants of the first light that shone in the universe. Right? Now, that light was once very, very hot, very bright. The temperature was very high. But then space itself started expanding, the expanding universe. And slowly, because of the expansion of space time, uh, these photons, their wavelengths got stretched out, and now they are in the far infrared, very, very, very low energy photons, 2.7 or so Kelvin. Don't quote me, 2 point something Kelvin. Very, very cold, very low energy, far infrared, and that is essentially the temperature of space, 2 point something Kelvin, which is close to 0 Kelvin, extremely cold. That's what it is. Yeah. So that is the temperature of space. Okay, Dr. Nishchay says Ayurvedic medicine is mostly dismissed as being herbs, rubbish, non scientific by modern medical practitioners. What's your take and experience on Ayurveda, and why is modern medicine having so much hostility towards Ayurvedic medicines? Why is it even a separate medical branch despite having active ingredients? Why is it not clubbed under evidence based medicine? It's not a scientific thing. It's There is a hostility towards Indian culture and Indian traditions. And that is why Ayurveda is dismissed. But they then use Ayurvedic uh, knowledge but rebrand it. For instance, you have something called pranayam, which is not Ayurveda, which is Indian tradition. We have something called pranayam. The West has rebranded it as cardiac coherence breathing. It is nothing but pranayam, but they are rebranding it, repackaging it under this new name, cardiac coherence breathing. And similarly, various Ayurvedic herbs like Brahmi, for example, have been rebranded as Bacopa monieri or something. And there is research being done on their active ingredients. It is being now uh, used as a so-called nootropic, something that can enhance your cognitive powers and intelligence and brain power and all that. There is research that's being done on various Ayurvedic well-known herbs, but they will all be rebranded as something non-Indian. So it is the hostility is not towards Ayurveda itself; it's towards Indian culture. It's towards Indian traditions. India is the oldest known civilization. India is the oldest continuously existing civilization, and the West resents that. Yeah, there's a whole different story to that, which we will not talk about over here. So it's not really being dismissed. Lots of research, I believe, is happening, but it will not be. Whenever some breakthrough happens, whenever they isolate the active ingredient, let's say curcumin, which is what is called haridra in Sanskrit, you know, it will be rebranded as something else, and most people will not even realize that it's something that came out of Ayurveda. So that's how it is. So what needs to be done? India needs to create its own scientific institutes of Ayurvedic research. Very simple. And whatever breakthroughs happen, patent them and make sure that they are attributed to Ayurveda. Whatever others do, it's something we can't control. And it's something we should not complain about. Why doesn't India start its own research institutes for Ayurvedic research? You research the various Ayurvedic herbs and compounds, etc., using 21st century scientific methods. Isolate the actual active ingredients and patent that and commercialize it if required, or make it available for free to people, whatever. So India needs to take steps to safeguard its heritage. The West is under no obligation to give India any. See, there is no justice in the world, right? People take what they can. So it's up to us whether we want to allow people to take everything that we have created. So yeah, that's how it is. It is certainly evidence-based medicine. It is certainly something that's been around, that's been proven to work for thousands of years. It doesn't work in the allopathic manner that you take these doses for like 5 days and you're done. This is something that is part of a lifestyle, but it does work. And if you can isolate the active ingredients in various compounds, various herbs, whether it is Arjuna, whether it is Brahmi, whether it is Guduchi or whatever, you could actually make massive medical breakthroughs. I'm sure it's possible. So India needs to take the lead in this. The Indian government should create national institutes of Ayurvedic research. The research should be done using 21st century scientific methods, and all of that should be patented, and it should all be branded under the umbrella of Ayurveda. That's what needs to be done. So that's what I can say. Next question. Won't appear. Okay, here it is. So this is by Atmaj. What's your take on energy beverages? Is it superior to tea? Tea, coffee contain so coffee contains caffeine, which is known to be a stimulant, or I don't know what category it falls under. But yeah, it keeps you awake, it makes you alert and all that. So that's caffeine, that's from coffee. Tea contains tein, which has a similar effect. It kind of perks you up, it makes you more alert, more active, but it's not as strong as caffeine as far as I know. Yeah. So tea and coffee are both stimulants, and they make you more alert and all that. Energy beverages don't, I think, in most energy beverages, two examples are Red Bull and Monster Energy. Both of these drinks, the main active ingredient is caffeine. I think they contain massive doses of caffeine, maybe 200, 300 ml of caffeine per can. And that's typically what perks you up and what gives you the energy, as to say, so to say. There could also be some other compounds like citrulline maleate or beta alanine or something like that. I'm not sure what it's called. So they could also have some kind of effect of giving you some energy or some focus, things like that. There's also this class of products called pre-workout supplements. Yeah, that kind of rev you up or something. I think these things, you develop a tolerance to that. I'm sure you even develop a tolerance to caffeine and tea over time. So I think these are the main ingredient in most energy beverages is anyway caffeine. So I don't think it's superior to tea or anything. People enjoy tea because tea is rich and complex. There are so many different varieties of tea. You have green tea, you have red tea, you have brown tea, black tea, and all that. The different flavors of tea. You can put various different spices into tea, cardamom and various things. There are all these various spice compounds, spice mixtures you can add to tea and make it more aromatic, more fragrant. So I think tea is a very rich thing. These energy beverages, they're like shortcuts. It's like injecting something into your body. It works for a while, but you don't get the enjoyment that people who are tea connoisseurs would get out of tea. So I don't think it's superior to tea. People who need a pick me up or something could do that. Take a shot of caffeine. There are caffeine pills available that would work even better, I suppose, or just have a black coffee or something. So it's at the end of the day, it's all up to you, what you enjoy, what you like, and what works for you. Yeah. So I don't think anything is superior to the other. Whatever works for you is superior for you, and that's what matters. So it's something that's an individual choice and preference. Atmaj again. I know this is not gonna get answered, but do you watch anime? Omae wa mou shinderu. Nani? Do I watch? Not really. I don't get the time. But yeah, I must have watched some anime in the past. Okay, that brings us to the end of today's questions that I had picked up. Let's take some questions from the live chat. A few questions from the live chat. What do we have? I had many more questions, but we are almost at the end of our time, so I'll take some live chat questions now. Okay, Bolly MV says, what's the difference between an asteroid, a comet, and a meteor? Let me also add one more, meteorite. So what's an asteroid? An asteroid is a rock that's floating around in space. It's orbiting the sun. That's an asteroid. So you have various classes of asteroids depending on where they're located in the solar system. You have the standard asteroid belt between the orbits of Mars and Jupiter. So you have the inner planets, the terrestrial planets, which is Mercury, Venus, Earth, and Mars. These are the innermost orbits. Then you have an asteroid belt between the orbits of Jupiter, between the orbits of Mars and Jupiter. That's a collection of space debris, rocks. So those are called asteroids. You also have a bunch of Trojan asteroids, which are at the Lagrange point of Jupiter. That's a whole different story. So these are essentially space rocks, big space rocks or small space rocks, tiny ones. These are all called asteroids. Typically, an asteroid is something which is reasonably large. Yeah, rock sized, boulder sized, building sized. These are asteroids. The largest asteroid I think is Vesta. It's like a small mini planet kind of thing. Yeah, that's what an asteroid is. What's a comet? A comet is a dirty snowball. It's composed of rubble. There is some rock, there is some soot, there is some dust, and there's a lot of ice, water, snow, and there could be organic compounds also in that. Yeah, so that's what comets are. They are essentially dirty snowballs, ice, snow, and water, frozen water, mixed together with some rock and some dust and some chemical organic compounds. And comets, when they also orbit the sun in various elliptical orbits. Some are small orbits, some are enormous orbits. Some comets may approach the sun once in 3,000 years, once in 80,000 years. Some comets go around the sun every few decades, and so on and so forth. So when they approach the sun, because of the heating effect of the radiation pressure of the sun, of the solar wind, the water heats up, it evaporates, and it produces this long tail like structure that is visible from the Earth, and that's what we call comets. What's a meteor? A meteor is a space rock that enters the Earth's atmosphere and burns up at that atmosphere, so-called shooting stars. What's a meteorite? It's one of these space rocks that doesn't burn up, but which does burn, but ends up impacting the surface of the planet, whether it's over the oceans or on ground. Yeah, so that's the difference between asteroid, comet, meteor, and meteorite. All right, I hope that answers the question. Let's take one or two more questions about science. Is human cloning justified? I think it's unethical to clone humans, because you're creating humans for your own agendas and purposes. Human life, I mean, from the perspective of ethics, is something that's inviolable. It's sacred. You cannot mess around with it. You don't own humans. If you're cloning a human, you're kind of creating a human tailor made to your specifications, and you're in a way owning it. You hold that person's life in your hands, so to say, which is clearly unethical. So when it comes to medical ethics, human cloning is considered to be completely unethical, and it's illegal in most places. I'm sure some nations are tinkering with certain things, but I personally would consider it to be unethical. Yeah. So yeah, I would say it's not justified. It's not something anyone should do. Um, Sajad says, "Do you think evolution really happened?" Well, the best evidence that we have from the fossil record and everything else does indicate that evolution happened. Look at the fossil record when it comes to human species. We have Homo sapiens. The oldest evidence is from about 300,000 years ago. Yep, the oldest fossil evidence of Homo sapiens is was discovered in Jebel Irhoud in North Africa, Morocco, I think, Algeria, somewhere there, 300,000 years ago. That's how old it is. Before that, we have had so many other archaic species of humans: Homo erectus, Homo habilis, Homo neanderthalis, Homo florensis, and so on and so forth. Denisovan also. And then you had older forms of humans, more archaic humans, or Australopithecus, Ardipithecus, and so on. So you can clearly see that there's evolution happening, and the morphology and the shape of the bones and the abilities, the cranial capacity, all of that is changing over time. Even the eyes have moved to the front. Our deep ancestors who lived like 60 million years ago had eyes on the sides, yeah, and so on. You can see how dogs have evolved. We can see that dogs are the same species as the wolf, and the foxes are related to dogs. Jackals are related to dogs. Wolves, foxes, dogs, jackals, very close together and very similar. Bears are a distant relative of dogs. Seals and whales are also related to the dogs, the same extended family. And you have cats that have evolved over time. So you can see that evolution has actually happened. And you can see it date back millions of years, even billions of years in the fossil record. So from all the evidence that we have of experimental evidence, hard evidence, empirical evidence, it does appear from all this evidence, to the best of our knowledge, that evolution really did happen. Right? Okay. Choose one, math or physics. It's physics. Math is a tool. As far as I'm concerned, physics is what actually makes things interesting. Math is about categories and logic. Physics is where you actually apply it to the real world. So for me, it's physics, but some people enjoy math, which is perfectly good. Okay. Which branch should I take to become a theoretical physicist in BTech? If you're doing a BTech, you're in a technical field, technological field. You're studying to be an engineer. If you are studying engineering, you can certainly go back into theoretical physics, but I don't know what advice I can offer you, because I don't know you personally. I don't know what your aptitudes are, what your strengths are. If you want to become, see, what kind of person becomes a good theoretical physicist? First of all, you need to be good at math. That is a given. You can't do theoretical physics without being really, really good at advanced mathematics, not basic math, really advanced mathematics. Yeah. So you should be able to quickly pick up mathematical tools. That's number one. And secondly, you should be curious about the mysteries of the universe. That's what theoretical physics is all about unraveling and demystifying the universe. Yeah. Uh, so typically, you would need to have the the the, the the mindset of a detective, of a very curious detective. Wow, look at this mystery, let's figure it out. If you have that approach, then you would be a good theoretical physicist. And you may have that curiosity and fascination, but if you are not good at math, then you still can't do it. So yeah, that's what I would say. First of all, you have to ask yourself if that's who you are, if that's the kind of person you have. If you're doing a BTech, then you may not be able to get into theoretical physics. So typically for a theoretical physics career, you would need to have BSc, MSc, then PhD or something or like that. Yeah. If you want to have a career within the academic system. So yeah, that's how it would go. Chiching says, how to have a sharp mind and not be forgetful. Um, you cannot have a sharp mind if you are physically unfit, first of all. So you need to take care of yourself physically, stay physically active, physically fit. Don't eat too much. Don't become obese or overweight. That's first thing. Yeah. Secondly, not be forgetful. I am forgetful. I forget people's names and faces all the time. I may have met somebody 5 minutes ago. I may sometimes forget people's faces. So it's someone saying eat almonds. you know, I think if you want to have a sharp mind, Be curious. I'm sure you are fascinated with something or the other. Follow that curiosity, that fascination. And when you study stuff, always give yourself the permission to forget stuff. Give yourself the permission to forget whatever you don't find interesting. That way, you will pick up those things you find interesting, and those may be the important things. So yeah, that's how my approach has always been. I am a very forgetful person in a variety of things. I forget the faces and names of most people. Apologies in advance to those of you who I may meet in the future, and if I don't remember you, yeah. So some people naturally have sharp minds. I don't know. I'm not one of them. I forget things, but stay physically fit, stay physically active. If you work out regularly, you're gonna have a sharp mind for sure. Eat well, eat good food, eat lots of vegetables, and good amount of protein goes along with that, protein of your choice. And when you study, give yourself the permission to forget. Only remember what you find interesting. That way you'll do well. Yeah. And yeah, some people would say meditate. That helps. Yeah, meditation also helps. And in case you have a restless mind, write. Writing calms your mind down. It focuses your mind. So if you have a writing habit, write 1,000 words a day, whatever topic. So that could sharpen your mind further. Writing crystallizes your thoughts and so on. So yeah, these are some of the things I could tell you. I hope that helps. Chiching. Okay, I think we are done for today. We have crossed the 2 hour mark as always. So yes, thank you so much for all your questions. Always great fun answering your questions. I apologize to those of you whose questions I've not taken. I'd taken many more, but I always run out of time. So we'll keep on doing this, and I will see you very soon in the next chapter of the Ask Abhijit show, which is tomorrow. Tomorrow is a different topic: geopolitics, history, and current affairs. But we will keep on doing the science sessions weekly, and let's keep on doing this. Thank you very much. Take care, all of you. Do very well, and I will see you in the next episode. Thank you. Bye bye.